There's been ongoing research here at Georgia Tech on puppies' behavior when playing. More specifically, the research found a positive correlation between specific styles of play and how likely puppies were to succeed in training programs for jobs such as service dogs and police dogs. This research is being performed with made in-house rubber balls utilizing barometers and accelerometers inside. These tools are used to gauge the force of the bite to make predictive models to forecast the puppy's success in the aforementioned training programs, and did so successfully with 87.5% accuracy. This semester, the aim of our research is to develop a way to analyze this data using audio, such that these tests can be ran with cheap, off-the-shelf squeaky toys rather than the time-intensive rubber balls made in-house. So what is the motivation behind this research? For starters, as mentioned in the original research paper, using methods such as these across the industry to identify dogs who will fail early in their training can save upwards of $5 million annually. More specifically, as it relates to our work this semester, our aim is to eliminate the need to use time and money making the rubber balls in-house. Alternatively, using off-the-shelf toys will make the test more accessible to more people because they're cheaper and can be found everywhere. This will not only make it easier for this process to proliferate throughout the industry, but can also lead to more data collected, which can make the algorithm more accurate. Here's our prototype setup. Here we have two squeaky balls that we got off the shelf and a load cell. And what we're doing is we're matching the balls into the load cell to produce a squeak, and we can read the exact force used to produce said squeak. And how we do that is through this breadboard that is running into, we have a microcontroller and an analog to digital converter so that we can get all of our information onto our laptop live. And over here we have a microphone set up so that we can read the frequencies of each squeak and match them up to the force used to produce them. We had multiple iterations on how we were going to collect the data on the force incurred by the ball to produce the squeaks. Originally, we were going to use the same method that they used in the original paper to calibrate the barometer and accelerometer in the rubber balls, which is to drop a known weight from a known height and calculate the force that the ball would incur. However, we didn't feel that this captured the necessary force and mechanical motion that a dog's bite would have. Our next iteration was to use the load cell that we made along with the CNC machine. More specifically, we made G-code such that the CNC machine would mash down on the balls into the load cell to produce a squeak. But we found that the CNC was too slow and that the sound produced wasn't like that of a dog biting on the dog toy. Now, we're just using our hands and mashing the balls into the load cell.
As for the results we have gathered so far, we were able to collect audio samples of the ball squeaks to the microphone, along with the force applied onto the ball to generate the squeaks through the load cell sensors. With this data gathered, we will attempt to synchronize both audio and force data in order to evaluate the relationship between the force applied to the ball and the pitch produced. Ideally, there will be a difference in the pitch depending on the force, which will simulate the bite force of a dog playing with a toy. Ultimately, we hope to utilize this information to create an audio recognition tool that is capable of distinguishing squeaks from other noises.